Hello everyone, I'm Lawrence from Extrapy. Welcome to Module 2 of our Cairo auditing course. In this we're going to look at some of the key Cairo language features such as ownership, structs, etc. Also the differences between Cairo and Solidity. If you're coming to this course knowing Solidity, then it's good to know the differences that you're going to see in Cairo. But this module is not intended to teach you to be a Cairo developer. If you're interested in that, please do contact us. We can help you with that. But it's to try to show you the details of the language that you're going to need to understand when you're auditing Cairo contracts. So I've got a couple of memes here for you. The first one here came out with Cairo 0 because it was quite a difficult language to develop with, and the people at Starknet put a lot of work into improving the developer experience with Cairo 1. And so Cairo 1 came out, it was based on the Rust syntax and it was a great deal easier to develop than with Cairo 0. So that meme should soon be retired. We then got another meme about the fact that Cairo code then needs to be upgraded. But again, we're past all of this, and so both of those memes should be retired. So the Cairo, the language, is designed to give us provable computation, which is what we need when we are using it as part of a validity roll-up because Starknet is a layer 2. It's a Turing-complete language, and it can be used as low level, and it has a particular memory model, that's sort of read-only non-deterministic memory. When we're looking at Cairo contracts, we don't need to really worry about this too much. It's under the hood, and but we're working at a much higher level. It is also possible for us to write Cairo programs which are stateless, but Cairo contracts do have state. Obviously, we want them to have state. We want Starknet to have state, and so therefore the contracts need to have state. This is provided by the Starknet operating system. If you want to dig into the language in a lot of detail, there's a white paper linked there. It is reasonably easy to read, although it was written about Cairo 0, so it doesn't describe the changes that have happened since then. Okay, so let's carry on. So what happens when we write our code? We start off writing Cairo code at a fairly high level. That gets compiled down to something called Sierra, which is an intermediate representation, and then that is compiled down to Chasm. This intermediate representation was introduced with Cairo 1, and it was introduced to address a problem that we had, that transactions in Cairo 0 were not always provable. In particular, if the transaction had failed, we couldn't prove that it had failed. And so the Sierra representation was introduced to fix that problem. And the Sierra bytecode, as I say, cannot fail in the sense that we can always prove if the transaction has failed. We're able to use it to count the gas, and it compiles down to Chasm. If you want some good documentation, there's the Cairo book. There's a link there to that, which is a very good resource. It takes you through the basics of the language and both programs and contracts. The language was designed to be effectively a virtual CPU, and it in doing this, it very much had the background of zero-knowledge proofs, and so it's working on that framework, and we do need to be aware of that. And when we're looking at some of the security aspects of the Cairo contracts, we do need to be aware that we are doing the computation, but in the context of zero-knowledge proofs and some of the restrictions that they provide. And we'll be talking about those general types of restrictions a little bit later. The language, though, is based on Rust syntax and semantics, although you shall see in a moment there are some differences. Now, if you're familiar with Rust, you will be familiar with the concept of ownership. And in Rust, this is there to make sure that we have memory safety and that we can have safe concurrency. And we have a similar concept in Cairo. And so we use ownership, but this is also needed to make the code provable and to ensure that the memory model is correct. So in Cairo, any value that we have, whatever type that is, even basic types, must be used exactly once, which means that it must either be destroyed or moved. Moving is similar to the move semantics in Rust, and it involves passing a value to a function, say. And then the other type of way it could be used is destruction, which means the variable goes out of scope, or a struct is destructed, or that we explicitly use the destruct function. Values in Cairo are immutable, which allows them to be safely referenced. Variables, though, can be mutable, and that's why we need ownership rules with them. Talking of references, we have the potential for snapshots in Cairo contracts, and this gives us a view of the state of the contract at a particular time. It is immutable, and to get the snapshot, we use a particular operator. As you see here, the @ symbol is used as a snapshot operator. There's an example here of it being used as a parameter. So we're passing an array into this function, but we're passing a snapshot of that array. And the opposite of the snapshot operator is the dsnap operator, and it allows us then to convert a snapshot back to a normal variable, and this is the asterisk symbol. And you can see it being used in this code, where we have a snapshot being passed into the function, this rectangle snapshot, and then we can desnap it by using the asterisk in front of this, in front of that variable. But also in this case, we're also using the asterisk as the multiplication operator. So do be aware that it can look a little confusing, but the asterisk can have two roles. So yeah, be aware of that. Okay. Let's move on to structs. Quite similar to what we would see in Rust. It allows us to group together values of potentially different types and create from that a data type. So we need to define the struct before we can use it, and then we can create an instance of it, and we use this struct keyword to do that. You see here we've got a struct user, and that has a number of fields of different types, and the difference between a struct and a tuple is that the fields within the struct are named. So you can see here we've got the name active as the first field within this user struct, and yes, you can see it being used here. We define our user struct, and then in our function we want to create an instance of this, and so we can use this syntax here. We use the name of the struct user, and then we use curly brackets, and then we fill in values for the different fields, as you can see there, and that will create an instance of the struct that we have defined. And then if we want to access the fields from the struct, we can use dot notation. So you just with your instance of the struct, you use the name of the struct, and then the instance of the struct, and then the dot, and then the name of the field to get the value of that field. Okay. We also have traits in Cairo, similar to Rust, although they do look a little different. And what traits allow us to do generally is to pull together types that have similar behavior, and it allows us to do this in a quite an abstract way, and allows our code to be quite readable and reduces boilerplate code. In order to use traits, we first need to define it. As you can see here, we define a trait called summary, and what we are doing here is saying that if you implement summary, then you're going to provide an implementation of a function summarize. So you can see here there's the function summarize, the signature of this being given. This takes a snapshot and returns a byte array. But it does. We're not providing the implementation of the function here. We're just providing the definition of. We're just providing the signature of the function within the definition of the trait. Once we've got that, then we can provide an implementation of it. So you see here we've got a struct called news article, which has a number of fields which are byte arrays. And then we are going to provide an implementation of the summary trait for this news article type. And so the syntax we use, you can see here, we use the import keyword, and we then have the name of our implementation, and then then we use of, and then the name of the trait that we are implementing, which is parameterized for the particular data type, as you can see here, the data type news article. And then within this implementation, we provide the implementation of the function that we gave a signature of in the trait. So you can see here we've got the summarize function. So we've got the signature matches what we have in the trait, but then also we provide the body of the function as well. So here this function is formatting some details from our news article struct. As you can see, we've got some fields from that, and then we're using the format macro to format those items and return them as a byte array. Similarly, you could do that with a different data type. We've got another struct here called tweet, and then we can provide an implementation of that. Using that, we can provide an implementation of summary, and you can see we have a different function, different function body, but same function signature. A very useful item from Rust and in Cairo is the option enum. And this gives us the possibilities for an optional value, and so provides us with a way to avoid lots of boilerplate code, and a way to handle potential missing values or null values within our code. So you can see here it's an enum. The possible values it can have are either some or none. If we have some, that means there is a value contained there, and this is going to be of the data type that we specify with our variable t here. So we're parameterizing this option type. We're using generics to parameterize it, and so the data type of the option when we create it would be the same as the data type of the value sum here. This can be used with things such as matching, and matching is very powerful. It's widely used in Rust, and we also use it in Cairo, and we can do quite a lot with the patterns that we are matching. This is quite a simple example, but you can see I've got an enum here called coin, which can take various values: penny, nickel, dime, or quarter. And then what I'm doing in my function here is I'm passing in an example or an instance of this enum. You can see here the variable is coin with a lowercase c, and then I'm matching that against some patterns. And so these patterns are the things on the left-hand side of the arrow here. And so we're going to match on either penny, nickel, dime, or quarter. And with the match statement, when you match against a pattern, then you follow the arrow and then you run the expression on the right-hand side of the arrow. So, for example, if we passed into this function a, say, dime, so coin, colon, colon, dime, then when we came to do the matching, it would not match on the first two patterns, but it would match on the third, and therefore we would then use the expression on the right-hand side of that arrow, which in this case is the numeric literal 10, and then that would be the value of the match block, so the item contained within the curly brackets of the match, and then because that is the last item within the function, then that is the return value of the function. So 10 would be returned is the return of the match block, and then that is the return value of the function. And matching is widely used in Rust and Cairo, and is often combined with the option and result enums as well, and we can do quite powerful things with that. So if you're coming from a Ethereum background, there are a number of things that you need to be aware of, the number of differences between Solidity and Cairo. And one of the most important is is about the data types, and in fact the native data type for Cairo, which is called a felt, which is a field element. So I spoke about the fact that we are doing our computation in the context of zero-knowledge proofs. So this is all based on finite fields, and we need to do that because we need to create a proof from our computation. But this introduces restrictions on the language, and if you look at other zero-knowledge proof systems, you will find similar things, that their languages are restricted, particularly the data types are restricted in their size. And with Cairo, we have a restriction because of the size of the finite field. We have a maximum size that we can have as our data type. So the native data type, the felt, has a maximum size, and this means that when we are using that and we are doing arithmetic with it, we're doing arithmetic that is mod this maximum size. And if you're doing additional multiplication, this is relatively straightforward, although you still have to be aware of the fact that there is a maximum size, and therefore because you're doing mod arithmetic, if you go above that size, then you will effectively wrap around, and so you will then start again at 0. So you have to be aware of that. Division is less straightforward, and this is because division is not as well defined in the type of operations that we can do with finite fields. And so you do have to be careful with division, that when you're doing a division, you're going to get the value that is expected. For example, if you divide 3 by 2, sorry, if you divide 6 by 3, you will get the value 2. But if you divide 7 by 3, you will get a completely different value, as you can see here. So you do need to be careful about division. And often what we do, rather than doing a division directly, we may provide a value that is the result, that we know is the result of that division, and then we check that in our Cairo program by doing a multiplication, and then that becomes something that is provable. Now, another point that you need to be aware of is to do with the size of the felt and compared to the size of the data type in Solidity. So in Solidity, we have a 256-bit data type, but in Cairo, the felt, the native data type, is 252 bits. So this is problematic when we try to mix those two data types. We would like to be able to pass 256-bit data items to or to use those in Cairo, but we don't have a large enough data type for that. The way that we get around that is to use two items within Cairo, and so we split our 256 bits into a low and a high part, and we have a struct that then contains those, and we can use that to represent the full 256 bits. And there are libraries that allow us then to manipulate this an instance of this struct, and will do, if for example if we want to do addition, it will do the addition correctly for us. Addresses are also different. In Solidity we have a 20-byte address which is derived from a hash of a public key. In Cairo the address size is different, so this is based on the felt, the native data type, and so we effectively get larger numerical values for that. The memory model is also different in the EVM. The EVM itself is stack-based, and we have a contiguous array for memory. In Cairo, the operations are performed directly on memory cells, but it follows this non-deterministic read-only memory model. So in the EVM, we can use operations like mload and mstore to write directly to our memory array, and that will grow as it is needed. In Cairo, it is different in that the memory cells are determined by the prover in the zero knowledge context of a prover, and once a value is written, it can't be changed. So memory is effectively immutable in Cairo. So it is handled quite differently, but that is quite a low level aspect. And typically, when we're looking at the writing Cairo contracts, we don't need to be aware of that. One other point, if you're thinking of writing Cairo, particularly with Cairo programs, is the fact that loops are handled or are more difficult to do. This is true generally of zero knowledge applications, that the loops tend to be difficult to implement. So we tend to prefer recursion. Other points, within contracts, variables declared in a struct when we're storing items, so when we have state within our contract, variables declared in the struct are not stored contiguously, but may be stored in different locations, and this is determined by a particular algorithm. So to find the value in storage for a particular variable, we take, for a single value, we take a certain type of hash of the variable's name. So this is a particular Starknet version of the catjack hash function. For more complex values, such as tuples and structs, etc., then the address is determined by the hash of the variable name, plus some other details. There's a link there to details of how that is done. And then for mappings, where we have a key value pair, we take a hash of the variable name, and then a hash of that and the key, and then we take a mod value of that. Okay, and we shall look at the issue of storage and how it is laid out, and the details of taking the hashes and the names, etc., because there is a particular vulnerability or there was a particular vulnerability around this. And if you want to get the address of a particular value in storage, then we have a function that you can call the address function, as you can see here. So if we have the myvar variable in storage, then we can get its address by calling that function. Okay, so that's everything from this introduction to the Cairo language as Module 2. We also have some further details of the language within some Starknet videos, which you will see next. So thank you, everybody. I hope you enjoyed that, and I look forward to speaking to you again in Module 3. Thank you.